Imagine a planet so far from its star that it's barely warm enough to exist. But this isn't just a cold world. It's a cosmic mystery wrapped in light. As it moves in its slow, distant orbit, it creates a rare and beautiful phenomenon. A tidal tail. A stream of gas and dust stretching out behind it. Though we can't see them with the naked eye, these tails are detected by the subtle changes they make in the light of their host star. This is the strange and beautiful world of transiting exoplanets, where we peer into distant systems and uncover their secrets. In the next few minutes, we're diving into the science of these tidal tails and how they help us understand the universe beyond our own. So what exactly are we talking about? Let's start with the basics. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. This is called a transit, and it's how we first discovered exoplanets. But here's the twist. As the planet orbits, it also stretches the star's gravity, causing a gravitational pull that can create a faint, elongated tail of gas trailing behind the planet. The size and shape of these tails depend on the planet's mass, its distance from the star, and how fast it's moving. It's a cosmic dance of gravity and motion. These tidal tails are not just beautiful. They also key to understanding how planets form, evolve, and interact with their stars in the vastness of space. You might not think about planets orbiting distant stars, but these tidal tails could hold secrets about how planets form and evolve, like cosmic fingerprints. Studying these tails could help us understand the gravitational dance between planets and their stars, revealing how planetary systems are shaped over time. By analyzing these tails, scientists can infer the mass, orbit, and even the age of a planet, giving us a window into its past. And if we find a tidal tail that behaves differently than expected, it might be a clue to something entirely new, like a hidden planet or strange force in space. So even if you've never thought about exoplanets, you should secretly care, because these tails could rewrite what we know about planets and their worlds. Back in 1995, we discovered the first exoplanet around a sun-like star, 51 Pegasi b. It was a gas giant, and it opened the floodgates for planetary science. Soon after, astronomers started looking for signs of planetary atmospheres, and that's where the idea of transit came in. When a planet passes in front of its star, it dims the light slightly. By the early 2000s, the Kepler mission was launched, and it changed everything. It stared at the same patch of sky for years, looking for tiny dips in starlight. Kepler found thousands of exoplanets, many of them in the habitable zone. And with every new discovery, we got closer to understanding tidal tails and their role in planetary evolution. Now, we're using next-gen telescopes like JWST to look even deeper. We're studying not just planets, but their tails, their atmospheres, and the forces that shape them. Imagine you're on a space roller coaster, zooming around a star, and suddenly, you feel a gentle tug. That's a tidal tail. It's like the star is pulling on the planet, stretching it out a little. These tidal tails are like a planet's own space scarf, made of gas and dust. They glow faintly, like a shimmering ribbon in space. We can't see these tails with the naked eye, but scientists use powerful telescopes to catch a glimpse of them. It's like looking at the planet's invisible clothes. Tidal tails are one of the coolest things about space, proof that even planets can be pulled and stretched by the gravity of their stars. To begin, we need a star with a planet in orbit, usually a close orbit. These planets are often called hot Jupiters, because they're gas giants that orbit very close to their stars. As the planet orbits, it passes in front of the star, blocking some of its light. This is what we call a transit. The timing and depth of the light dip tell us a lot about the planet. But to detect the tidal tail, we also need to look at the gravitational influence of the star on the planet. This causes the planet to stretch, forming a tail of debris and gas. This tail is not visible in optical light, but it can be detected using specialized instruments that measure the emission from ionized gas and dust. The tail is a direct sign of the planet's tidal interaction with the star, giving us a window into the planet's orbit and its potential future evolution. Once the planet passes in front of the starlight dims just a tiny bit. This dip is our first clue that something is there, but it's not enough on its own. But what really matters is how the starlight changes as the planet moves across the star's surface. This is where we start to see the shape of the light curve, which tells us about the planet's size and orbit. This tilt is crucial, because if the orbit is edge-on, we can see the planet passing in front of the star. But if it's tilted, we might miss the transit altogether. To confirm the planet's orbit and tilt, we analyze the shape and timing of the light curve. This helps us understand not just the planet, but also its parent star's properties. This step-by-step process of analyzing the light curve is how we can discover new worlds, even when we can't see them directly. Now comes the clever twist. We don't just look at the star's light, we also track how it changes as the planet moves. This is where things get really interesting, because the starlight doesn't just dim. It shifts in subtle, predictable ways that reveal the planet's true shape. The key is that the planet isn't a perfect sphere. It's squashed at the poles, like a spinning jelly. This makes the dimming pattern not just flat, but a bit wobbly, revealing the planet's shape and rotation. By measuring these tiny changes in the light curve, scientists can actually map the planet's shape, even from light years away. It's like reading the planet's heartbeat through the star's glow. This method, called transit timing variations, is a powerful tool that allows us to see beyond just the planet's size and distance. It gives us a glimpse into the planet's internal structure and how it spins. So, the clever twist is not just about detecting the planet. It's about understanding its form, rotation, and even whether it's spinning on its axis. It's like reading a book with just a flashlight and the flicker of light. Underneath all the drama of a transiting exoplanet, there's a precise physics engine at work. Tidal forces, orbital decay, and gravitational resonance. These are the silent rules of the cosmic dance. The planet's gravity stretches the star, creating tidal bulges that emit faint light. These are not just visual effects. They're a measurable signature of the planet's presence. As the planet orbits, these tidal bulges shift, and the resulting light curve can reveal the planet's mass, orbital period, and even atmospheric composition. But tidal forces don't just affect the star. They can slow the planet's rotation, synchronize its orbit, or even cause it to spiral in over time. It's a dance of gravity, not just light. Tidal tails are just the visible tip of a much deeper, more intricate astronomical process. Imagine if the Earth was a spinning top, and the Sun was a heavy weight pulling on one side. As Earth orbits, the Sun's gravity stretches it like a rubber band, creating a bulge. Now, imagine this top is orbiting another star, and as it moves, the star's gravity keeps stretching it, like a balloon being pulled from one side. This tiny dimming is what astronomers call a tidal tail, a gravitational shadow caused by the planet's own gravity being pulled by its star. It's like watching a heartbeat. Every time the planet orbits, it briefly hides a small part of the star, revealing the invisible force of gravity at work. Before you go, if you enjoyed this, please give it a like and subscribe so you don't miss the next one. And tell us in the comments what you'd like us to make next. We read every single one. Thank you so much for watching. Comment this emoji if you made it to the end.